Quicksort is a sorting algorithm. That is, it takes an array of values such as this one as input and it permutes them such that they end up in increasing order. Quicksort is one of the more interesting sorting algorithms, and it is a little bit like a rocket in that it is very fast, but very few people truly understand how it works. Let us illustrate the main idea behind Quicksort on our earlier example. The first step in Quicksort and most of the hard work in it is in the so-called partitioning. To partition an array, an element is arbitrarily chosen and called the pivot. There are many strategies for choosing a pivot, but for simplicity, let us always choose the leftmost element. The goal of the partitioning is to move all elements smaller than the pivot to the left and all elements larger than the pivot to the right. The elements on either side of the pivot are allowed to be in any order whatsoever. What is important is that the elements on the left are smaller than the pivot and the elements on the right are larger. Note that after partitioning, the pivot is in its final position as it would appear in the sorted array. Furthermore, the elements to the left of the pivot remain to the left in the sorted array, and the elements to the right of the pivot remain to the right of the pivot in the sorted array. This allows us to concentrate our attention on the range to the left and on the range to the right of the pivot individually. We first sort the left-hand side using a recursive call. Afterwards, the right side is also sorted recursively. Let's make a first try at partitioning an array. If we had additional memory, say for 2 extra arrays, partitioning would be very easy. We would simply walk the array one by one and save the elements smaller than the pivot into the second array and the elements larger than the pivot in the third array. At the end, we would find our partitioning by combining the small elements, the pivot, and the large elements in this order. However, one of the defining characteristics of proper quicksort is that it works in place. In place means it does not use much memory in addition to the memory occupied by the input itself. Instead, the input array is used for temporary processing as well. To partition an array in place, meaning without using additional storage, there are several strategies. I'll show you the simplest in-place strategy for partitioning. We use 2 indices, L and R, that satisfy the following property. The pivot is at position L, everything to the left of L is smaller than the pivot, and everything to the right of R is larger than the pivot. For the elements marked question mark, we do not know anything yet. The idea is to shorten the interval LR until it contains only the pivot. Initially, L points to the first element and R points to the last element in the array. We now take steps that decrease R or increase L to make the interval LR smaller, until only the pivot is in the interval and thereby L equals R. If there is an element larger than the pivot at position R, we move R towards the left. This ensures that to the right of R we only have elements larger than the pivot. Otherwise, if the element at position L plus 1 is smaller than the pivot, we swap the elements at position L and L plus 1 and increment L. This ensures that to the left of L, we only have elements smaller than the pivot. If none of the 2 operations above can be performed, like in the picture above, L plus 1 points to an element larger than the pivot, and R points to an element smaller than the pivot. It would be useful if it were the other way around, since then we would have just skipped over the 2 elements in the previous steps. Therefore, in this third case, we simply swap L plus 1 and R. The interval LR remains the same in this third case, but we are sure to lower it in the following 2 steps at least. We repeat the procedure above until L equals R. Decrease R as it points to an element greater than the pivot. Increase L and move the pivot towards the right as long as L plus 1 has elements smaller than the pivot. At this point, we are done. All elements smaller than 7 are to the left, and all elements larger than 7 are to the right. Let's go ahead and implement Quicksort in C. We illustrate the implementation using our running example shown above. Let us write a function sort that takes an array A and its size n as inputs and sorts the array in place. Recall that the Quicksort algorithm is recursive, and that the recursive calls could sort arbitrary subarrays of the initial array. Therefore, we need an auxiliary function that we call sortRange. It takes as input the array A and the range given by the index of the first and the last elements in the range. The purpose of sort range is to do the hard work of actually sorting the range of the array A between indices first and last inclusively. The function sort then simply calls sort range for the entire array. Going back to sort range, it is a recursive function implementing the quicksort algorithm. As with any recursive function that terminates, we must have some base case where recursion is not necessary anymore. The base case is represented by ranges having 0 or 1 elements, as these ranges are already sorted. We check if this is the case by seeing whether the index first is equal or past the index last. For the base case, there is no work to do. For the recursive case, recall that we first need to partition our subarray. We define a function partition that partitions the subarray given as input and returns the position of the pivot after partitioning. Assume for a second that partition is done. How do we use it to fill in our sort range function? In the recursive case, we must first partition the array, and therefore we call the partition function. This brings the pivot to the index position in the array. This is, as discussed, the final position of the pivot in the sorted array. What remains to be done is to sort recursively the range on the left-hand side of the pivot and then the range on the right-hand side, making sure to exclude the pivot in either case. It remains to fill in the partition function. We make use of the auxiliary function swap that should be self-explanatory. In partition, we initialize L and R, as explained earlier, by the first and the last position of the range to be partitioned. The pivot is always at position L. We now loop until the interval between L and R shrinks to just one element, which is necessarily the pivot. If the rightmost element is greater than the pivot, we simply decrease R. If the leftmost element just after the pivot is less than the pivot, we swap it with the pivot, making sure to update L accordingly. Finally, the interesting case is when none of the conditions above hold. In this case, we swap the rightmost element in the interval with the element just after the pivot. This enables the following iterations of the loop to shrink the interval between L and R further. Finally, we have to return the position of the pivot, which is necessarily at index L. Consider liking this video and subscribing to the Truly Understanding Algorithms YouTube channel to stay up to date with our latest videos on fascinating algorithms and data structures. Also visit us at trulyunderstandingalgorithms.com to read this tutorial in textual form.